Now, this topic is called permutations and combinations. Now, I'm not going to define what those actually mean just yet. We'll get to that, okay? What I want to go is go back to our fundamentals. When we first started looking at numbers, we first learned how to count things. And that's exactly what we're going to do here. We are going to learn how to count things, okay? Now, what are we actually going to be counting though? We are counting numbers. One thing that we'd love to count back when I was in high school was iPhone codes. I don't know if it still does it, but when you punch in iPhone codes and you get it wrong, do you know what happens? It locks you out. And then if you try again and again and again, it locks you out for a longer and longer period of time. I always wondered how many possible codes were actually possible. Well, what's the chance I actually got it right the first time? 1 in 10,000. How do you get that? Magic. If you think about it, right, think about your possible passcodes you could have, 1, 2, 3, 4, I can have 0, 0, 0, 0. But the fact that these options are actually numbers themselves make it very clear how many possibilities there are. I can start from 0, 0, 0. I could go 0, 0, 0, 1.
So it's literally like the last password you can do, the highest one is how many?
And yeah, and I could do 9,999. I can go all the way up to there. So I have the numbers 1 to 9,999, but I've also got this one here. So as you said, there's 10,000 possible different codes that we could have. So 1 in 10,000 chance I'd actually get it right. Now obviously that increases the more digits you have. Now I think a lot of them have 6 digits, right? And we could work with that. But what I think is far more interesting to be counting is not just things where there are numbers as choices. That is actually a bit too easy. Why don't we look at something like this? What do I have here? I have our canteen menu. Banana bread, tortillas, and a bacon and egg roll. And we want our hearty breakfast drinks, Up and Go and Lipton, okay? Lipton iced tea. Now, these things, I can't really count them in this way, but I can still think about them. What did you guys do in order to think about the possible choices you could have? What did you guys do? I think you drew a tree diagram, right? You drew a tree diagram which said, okay, from banana bread, I can choose 2 possible things. I can choose Up and Go and I can choose Lipton. That's 2 things there. For this one, I could also choose 2 of those drinks, right? That's 2 choices there. And this one, I could choose the bacon egg roll, and I could choose these 2 here. That's 2 possible choices there. I can add those all up, and then I can get 6, right? Now, drawing that tree diagram is fine. It helps me see really clearly, what's actually happening here, right? What's the problem with the tree diagram there? Yeah, I'm going to start having all these lines, and the more choices I have, the more I'm going to have to draw up, and it's going to get very confusing, right? If I add in now the options of paddle pops, then I have to start thinking, oh, what about the paddle pops? I can choose, or maybe dessert, right? As I add in more choices and more options, right, then it's going to make things more tricky to do, particularly with a tree diagram. Let's give you another example. Let's go away from food for a moment. One thing that I like about uploading videos is I can see all the different outfits I've worn. And I've realized that I don't have too many outfits. In fact, I have 12 different shirts.
Not too many.
I have 5 different ties and 3 pairs of pants. So, how many different possible outfits can I wear? Now, I don't want to be drawing a tree diagram for something like this, right? Is there something else I can do here? Is there something that you realize? 180. How do we get that? Oh, so you realized that, hang on, if I go back to my food example, right? I don't have to draw this whole tree diagram. I can just think about how many choices do I have for this first kind of selection? That's 3. How many choices do I have here? That's 2. If I multiply them together, I get how many possible outcomes there are. Can we do that for this one as well? How many kind of like positions are there? Because if you think about this, right? This is like one position, it's breakfast. This is one thing, which is drinks. Can I do that for the numbers?
Yeah, there's a way.
Sorry?
For each
Ah. So maybe if we break it up, if you go back to the iPhone code, right? You can see that literally there's slots here. And you're going to see me doing this for a lot of these types of questions. I'm going to draw in these kind of lines, and they kind of represent these positions. And when I put a number here, it's telling me how many choices do I have. I can have any digit from 0 to 9. So how many choices is that for 1? 10, right? How many choices is it for the next one? 10, 10, and 10. If you multiply that all together, you actually do get 10,000, which is how many possible codes there are. So now here, I don't have to draw my tree diagram. What would I do? How many kind of positions do I have here? Well, I guess they're not really positions, are they? Like, how many kind of stages are there? There's 3, right? There's 3. Right? There's 3, so I can have a shirt, have a tie, and a pair of pants. How many choices do I have for each one? I have 12, 5, and 3. What do I have to do with these numbers? I just multiply them together. And in fact, I do have more than I expected. I have, that's 180? 180 outfits. So I can wear, for half of the year, I can wear a different outfit each day. How cool is that? This is what we call the fundamental counting principle. And I love it because it's something that you thought of intuitively and you kind of worked out yourself, right? Rather than like a formulaic, oh, this is what it is, right? You guys saw that yourselves. Let's write it down and formalize it though. So, fundamental counting principle. We're calling this the fundamental counting principle. And in a generalized kind of way, this is almost like a paragraph which explains how to use it. If I know something has A choices, and something has B choices, and C choices, I've written these dots on here because it doesn't matter how many of these kind of positions or selections we're kind of making, as long as I know the possible number of, as long as I know the number of choices for each kind of position, I can find the number of possible outcomes if I just multiply them all together, okay? And again, like I said, you'll see me writing these kind of lines to represent those selections I'm making. When I'm thinking about this one, I want a password, right? And I know a password, in this case, has to be 3 letters followed by 3 numbers. So how many of these kind of lines do I want to draw here? 6, right? 6. Now when I'm thinking about letters and numbers, well, how many letters do I have? 26. So I have 26 for that first one, 26 choices for this one, 26 for that one. How many numbers do I have again? I have 10, right? I always think about the digits from 0 to 9. 10, 10, 10. Now when you evaluate that, when you multiply these all together, what number actually is that? Can you read it out for me? I think it's quite large, isn't it?
1757.
Yep. 600. So what is that? 1,757,600. So you can see, just with 3 letters and 3 numbers, I can create this many passwords. Now how do you want to leave your answer? Sometimes they'll ask you to evaluate it. If you'd like, what you could do is, another way you could write it is, well, that's the same as just 26 cubed times 10 cubed. I'm also happy with that answer. Both of those are fine, right? If you want to save a bit of space. One thing I've always wondered is with like mobile phone numbers, is it possible to run out? Mobile phone numbers, they always begin with 04. Does anyone know how many digits there are in a mobile phone number? 10. So I need, how many of these spaces? Yeah. Okay, so there's 10 digits there in total, but with this one, there's almost a bit of a restriction here. These ones are kind of locked in. I can't do anything with those, right? So those are just there, I guess. I can't really do anything. Here, though, I'm still going to write how many possible choices I have for each of them. And just like with the digits over there, it's just 10, yeah.
Wait. 10 million.
Yep.
I think that one there has another O.
One more 0?
Yeah.
Oh, sorry.
17,500,000.
Okay, that's all right. There we go, we'll fix that up. 17,576,000. There we go, that's all right. Wait, is that right? Yeah, 17, yeah, cool, sweet. But I can still write it out like that, yeah. Okay, this one here, again, large number. I don't want to write that all out, so I'm going to say how many possible choices are there, or how many possible mobile phone numbers are there? It's just 10 to the power 8, right? And I can write it like that. So 10 to the power 8, that's a lot of people that we're going to need until we run out of mobile phone numbers, right? So probably not happening anytime soon. Binary. For people who do IPT, what's binary mean?
There's only 2 different options for each.
Yeah, and what are those options? 1 and 0. So in binary, we can only use 0 and 1. They represent true and false kind of thing, right? So, do they represent true and false? I don't know if they actually.
It means on and off.
On and off. Okay, something like that. Yeah, all right. So, 10 digits here. Same thing, right? I'm going to have, sorry, a string is just kind of a length, right? So I want to have 10 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many choices do I have for each spot? 2. And I want to multiply these all together. That's a lot there, but I can write that much more nicely as just 2 to the power 10. Okay? A lot of different choices there. Now, what about something like this? Imagine I had these cards here, 5, 3, and 1. How many numbers could I make if I have these cards and I just rearrange them? I've got 531 here. Let's move it around. Okay. So right now I've got 315. Okay. I could swap these around and I could have 513. This word with replacement, what does that mean though? And you've seen it in probability. When you think about probability, when you're like taking things out of a bag, you put it back in. What would that imply for this situation? I could, because these are like physical cards, right? Can you see if I don't kind of get another one, I've used up my 5 card. With replacement implies that I can actually get another 5 card and put it there. Or I could even get a third one and put it there and make 555, right? If I'm not replacing it back into my pile, okay, I wouldn't be able to make something like this because I would have run out of 5 cards. Does that make sense? Right? So with replacement, it's saying I can use these multiple times. If I am using it multiple times, think about it again. We've got 3 cards, so that's 3 spots. And it'd be 3 in each one. Can you see that? 3, 3, and 3. And again, we're multiplying all these choices together from the fundamental counting principle, and that's 3 cubes, right? Or 27. Can you see another pattern that's evolving within this? We are multiplying things all together, but what's the kind of shorter version of how I've been writing them? To the power of something, right? And how many powers do I have? I have number of spots that I'm using, right? And what is the base then? Like this one was 2, this one was 10, this one was 3. Where did I get those numbers from? How many choices? That's it. Okay, so this is something we can generalize, right? How many choices we have. And it only works in a specific situation. It's this idea of with replacement. Because these ones here, I can repeat the digits. This one here, I can repeat the digits. And this one, I was telling you that I could replace it with lots of 5s there. So it's a specific case, and this is what I want you to write down. So that is a kind of extension of the fundamental counting principle. I know I can just multiply things all together to find the number of possible outcomes, but I can make that a bit simpler. I can say, well, if I know it's with replacement, I can say that just r to the power n, where r we say is the number of objects that we have, and then I guess you want to think about it as the number of like positions or selections you're actually making, right?